Greetings and welcome. So in this video we're going to talk about an LRC tank circuit and specifically see if we can't begin to tease out and get to the bottom of what factors affect the Q factor. That's probably not the best way to put it, but what things affect the Q factor of your LRC tank circuit. Not to be dramatic, but I'll just say I'm going to go through this once, and then I probably won't return to this in future. So if I'm building things later, and it's sort of why are you doing it that way, it will go back to this video, and this may end up getting broken up even into 2 or 3 parts depending on how long I go on for. So let's begin. What is an LRC tank circuit? So here's the Wikipedia on LC circuit. So the L is the inductor, the C is a capacitor, and they have an arrow that's not a diode. It's just showing the direction of the current flow. And you could either stick a resistor in there, and that would be the R for your LRC, but all components, including your inductor there, will have resistance, as well as your switch will have on-state resistance. So what happens, this would normally be open. This capacitor would be charged to a voltage, say 10 or 20 volts, and then that switch is closed, and the capacitor discharges into the inductor. And what happens? Well, as the capacitor discharges, a magnetic field begins to form in the inductor from the current flowing through. And at some point that magnetic field becomes the strongest that it will be as the capacitor begins to discharge. And it is as though you are storing the electricity in the inductor. And the reason for that is because when the field strength of an inductor changes, per Faraday's law of induction, there's a current that develops. So what you see happen is the capacitor discharges, it goes to 0, and when it's at 0 is when you have your maximum field strength. But then it doesn't stop there. It keeps going, and it goes negative, and it'll go negative to maybe -1 volts, maybe -9 volts, maybe something different. And then when it's reached as negative as it will go, now the inductor begins decreasing in field strength, and current begins flowing back into the capacitor. But because the field strength is decreasing, it has an opposite polarity. So this will then end up at like -8 volts, as I just said. And then the -8 volts discharges, the capacitor goes with the field strength strengthening, and then goes back, and this goes to say 6 volts, and then -4 volts, and then 2 volts. And it rings back and forth there. And there's a little animated diagram they give us here. And you can pay attention to the positive and the negative on the capacitor, and you see that they're changing each time. One plate is positive, then negative, and then positive again. So when this cap discharges, that process of the current going back and forth, happens at a predetermined, well, if you calculate it, it's predetermined. It happens at a specific rate, and that rate is known as the resonant frequency of your tank circuit. And there's not anything you have to do. It happens at the resonant frequency. And what is the resonant frequency of your LC tank circuit? It is, if you want to do it in hertz, it's 1/2 pi times the square root of your induction times your capacitance. Or alternatively, if you wanted to know, how many milliseconds or whatever for this to complete one oscillation, it would just be 2 pi times the square root of LC. So just not to get off topic, but if you go to a setup like this where you have an alternating current going into something. Now here you would want to adjust the alternating current to where it's going in at the same rate that this process is going on. So you would be adjusting it to the resonant frequency. But when you have something like this where you just discharge the cap, it just goes at the resonant frequency. There's nothing to do. It's just that's where it goes. And then the question is, do you want to interrupt that process at different points along the resonant frequency? So we have, I might have just been saying this, but we have this situation where the capacitor discharges, the energy ends up in the inductor. When the magnetic field strength of the inductor changes, then energy is shot back the other way. The capacitor charges negatively, and the process goes on again at a specific frequency. And how quickly that dampens out is determined by Q factor. Now, I've seen multiple definitions of Q factor, but the idea is very simple and intuitive. So if we go here, again, this is Wikipedia, bandwidth definition. It's the ratio, how do they say it? They're saying they aren't exactly equivalent. That's not good. So it's the bandwidth definition. It's the resonant frequency divided by delta F, which is the full width at half maximum. So this sounds very confusing, but we'll talk about it again. It's actually very straightforward, and I like this definition. And then there's also a stored energy definition, energy stored over energy dissipated per cycle. And they give that formula, and I guess they give similar but not exactly the same values for Q factor. So if we talk about this one a little bit more, so I like this one where they're calling this the ring down method. This is very close to this bandwidth definition, and what they're saying is extremely simple. You have your cap discharge, and say you're at 1 volt. You count how many oscillations happen until you're down to 0.5 volts, and then you multiply it by 4.53 to find Q. And so they're saying here that this LC tank circuit would have a Q factor of 30. And so you can see that this is a very undamped oscillator. You know, if it had gone from 1 to, say, you know, negative 0.4 to 3, and that it would have died out like right there. This one keeps ringing for a while. And so that's nice. So in a moment here, we'll go back to this setup on the breadboard, and we'll demonstrate what was just talked about. And then also we'll see if we can begin to see what are the factors with the coil that lead to a higher Q factor or a lower Q factor. And what that would mean would be a less damped oscillation or a more damped oscillation. And I'll also say, just here in passing, not to get too far astray, all this time I worked on this, I had a specific idea that I looked into, and I'll go into this later. And it didn't work, and I have a much different, entirely different, not entirely, but I have a much different view of what's actually going on with the boost circuit that I hadn't really gotten before. So we'll talk about that as well. But I want to try to stay as focused and cogent as possible. So we'll get to that later. Now, before we even get started, we can make some guesses about what is going to improve Q factor, and they're pretty straightforward and obvious, and they held up very well. But nailing it down more precisely was why I did all of this. So the first thing is, if your coil doesn't have much inductance, let's just say you have a coil without much inductance, and you just hook it up to a battery and you leave it there for 10 seconds. The inductor eventually, you know, it stops increasing. It goes to its maximum strength there, and then, you know, it's just an electromagnet with a specific number of Gauss for the B field. So likewise, if you had, say, like a 1 farad capacitor, and you put it into a coil without a lot of inductance, then the thing will go down to 0.999 farads or something, and this will now be at maximum field strength. And after that, you know, it can't store any more energy. So, and the thing will go all the way down to 0, a little bit below it, and then there's just a tiny bit that can shoot back into that giant capacitor, because for most of the time the coil was entirely saturated at its maximum field strength. So the first thing is that you don't want to go to saturation. The second point is, okay, let's say you haven't just fully saturated the coil for, you know, 90% of the whole time, but is only going 1/10 of the way to saturation better than going half of the way to saturation, is only going 1/1000th better than going 1/100th. And if anyone watched the, you know, the spreadsheet presentation I did on instantaneous amp flow, which I noticed they're not. It's like Gimli. No one's asking me. We should go through the mines of Moria. Sorry. You can see just from the conventional equations that for a given expenditure of charge, let's say, you know, you use 10 coulombs of charge and you get a field strength of 10x. If you have a cap 1/10 the size and you use 1 coulomb of charge, you don't get a 1x field strength. You get something like a 1.5x. That continues on ad infinitum until you run into other factors. And I think the most important one there is the skin effect. So that's the first thing. You know, they always, you need a sharp transient. That's why you want a short pulse, is because it generates, per the amount of coulombs you're expending, a larger field strength. The ratio between field strength to coulombs expended keeps improving as you go faster and faster. So again, I did a presentation on that. And so one can say that one needs a small enough capacitor and or a large enough inductance that one is very early on in terms of the saturation curve of the inductor. Another factor is resistance. Now, I've mentioned, you know, previously that if you're just discharging one cap to another, resistance never leads to energy losses or power losses. You know, if you have a cap at 10 and equal size cap at 0, they both end up at 5 volts as their end state, whether there's 1 ohm of resistance or 1 million ohms of resistance. It's just how long it takes. With the 1 ohm there, you know, maybe it takes a couple hours or something, and the 1 or 10 or even 100 ohms, it's just there. But they both end at 5. So in that sense, resistance never leads to a loss of energy or charge. However, this is a much different situation, because the charge is being generated by the changing magnetic field. You know, it charges up the field, and then the magnetic field collapses and it goes back negative, and your cap goes negative. And so you have a limited time to move as much as you can to, you know, make the thing have a high Q factor. And if you have a bunch of resistance in the coil, then that greatly dampens things. So that is a situation where you lose charge and you lose energy primarily, entirely because of resistance. And as it turns out, what I'm beginning to see here is that resistance is the most important factor. And we'll talk more about that. And along with resistance, you also have to remember the resistance in the on state of your switch. So, as I mentioned previously, I had gotten very confused about something, and I was just trying everything, going back and forth, and so I went back to kind of, just went back to the beginning here. I put in all Comus AC37s, which I know how these things behave, the opto isolation. They don't have any weird, diodes or anything in the interior. And I know what to expect with them. And so that's what we have set up here. The problem is that you can't go over 30 volts with them. They have about 1 or 2 ohms of resistance in the on state, which you say, well, that's nothing. But what if your coil has 1 ohm of resistance? Now you've doubled the resistance. So, and you're trying to get the resistance low. So you don't want a coil with 50 ohms of resistance. You want a coil with 1 or 2 ohms of resistance. And then that 1 or 2 ohms actually, I'm thinking, will be a big deal. So, one of the next projects that I'll do will be how to, or I'll try to do, will be how to trigger a MOSFET with an opto isolator. One other point: if you just have a MOSFET off of your Arduino, it's not going to work. It just somehow it leaks out back into the Arduino ground, and so you never see this oscillation. So you either need it opto isolated. The other way you could do it, and I've done this, and this is why I video log this stuff. I'd say I'm 95% certain, 98%, but I did it a while back. The way that John Bedini triggers the 2 transistors with another transistor in the, I'm blanking on the other fellow's name, the bipolar commutation circuit of Bedini and the other gentleman. But that bipolar commutation circuit, if people have worked with that. So that's not opto isolation, but when you do that, then yeah, your cap you'll still see the oscillations there. So, oh boy, I'm like incompetent with a cell phone. There we go. Actually, it might have looked nicer. Whatever. So, induction L, resistance R, capacitance C, all factor into what your quality factor or Q factor is for things. Now, I'll just talk a little bit more, and then we'll fire something up, and then I'll show you some of the stuff from the spreadsheet as well. So the last sort of thing I want to talk about, and then again we'll fire something up. If you have a backwards diode coming off of the positive here, going out to another cap with another line going to this positive going to the negative of another cap, and then another line going out here. Now you have a buck boost converter, so that when you discharge this, you see voltage show up here. Now, how well you transform voltage is very contingent on whether you disconnect, you reopen this circuit, where you reopen it in the cycle of these oscillations. And I spent a lot of time mapping that. That was the series where I was doing the Arduino as a data logger. And I have a clear understanding, so I'll just tell you. Why don't you just tell me the name of the movie? So you have this thing going, 10, let's say -9, 8. When the capacitor gets to 0, when it goes from 10 to 0, is where you have the highest field strength. Now, when it goes from 0 to -1, current's still flowing here, but it's flowing less strongly, and so there the inductor is already beginning to weaken. So when this goes to 0, if you open it right there, that's where you get the best transformation of voltage and your maximal pulse into another cap. So what you have is you have this oscillation of the capacitor doing that, and then you have 90 degrees offset, because this goes from 10 to 0 to negative to 0 back to its highest voltage positive. So 90 degrees offset, you see a big spike in the voltage, and then it just sits at, it'll not quite get back to your input voltage, and then it'll spike again, although now your oscillations aren't as large, and then it'll sit there. Now, I don't know, even now, I have no idea why the cap doesn't go all the way to 0. Why you get anything. So just a few more things. Then I think that, when you're interrupting it there at 0, that again, electronics, I'm self-taught, but they talk about zero crossing circuits. So that's what I think I'm getting at, that this is, when you're interrupting it there, you're interrupting it at the 0 point. So my idea, and I really need to fire something up for you, but it looks like this will be multiple part video. My idea that didn't work was, I was saying, all right, this is going to go from 10 to -9. What if I just disconnect, say this diode going out to this other one, instead of disconnecting the cap from the inductor, just disconnect the diode right at the 0 point, and now you'll have your cake and eat it too, because now you'd have a strong pulse that transforms voltage very well, and then this is going to go back to -9. And so I did that, and it didn't work. In fact, it was spectacularly bad. When I interrupted this by disconnecting the connection to a gather cap at the 0 crossing point, it actually, nothing showed up here. It was like 0.1 volt instead of 5 volts or 8 volts. And I was thinking, is it something with the switches? It's going back to, ones that I'm real familiar with, is the timing. And then if I did it at other times, it would start to show something again. And I couldn't figure it out until, as sometimes often happens, I go to sleep and you quiet down from the day, and it's like, oh yeah, of course. When you disconnect physically the capacitor and the inductor, this inductor has all of this field there, but the generation then happens later. It happens subsequent. So if now you disconnect the connection out to your other cap, now the field collapses and it has nowhere to go. It'll just float around and maybe fry components or something like that. So that happens subsequent when the field is collapsing. Now, another thing, when you think about it, is that when you disconnect, boom, what you're doing, let's say you didn't disconnect it, then it would go down to 0, and then it would go negative to, say, -8 or 9 volts. If you disconnect it, then all you're doing is, instead of this changing magnetic field shooting back to here, now it doesn't have a connection to there, but you gave it a connection to another cap, and so it shoots out to there. So they're the same thing. You either disconnect it at the 0 point and you shoot the induction out to another cap, or you leave it connected and it says, okay, we'll go back to this cap. And in both cases, it's inverting. So that's why you have the backwards diode from the positive going to the negative, where here you would just see it shoots back negative and this cap goes negative. So now I have a couple other, projects that I'll work on going forward, and I'm a little more confident that one of or both of them will work. But they have what's called synchronous rectification, and there you get rid of the diode. So I guess one point is, and this is something I'm going to look at that I haven't looked at yet, maybe we'll look at it today, is if you disconnect it right at the 0 point, that'll be your best shot out to the cap. And you can look at what shows up in the cap and maybe get 5, 6, 7, 8 volts or whatever. Then don't shoot anything out to the cap. Just let it shoot back here. And what that will tell you is how much you're losing from the diode and whether that's significant or not. So maybe it's imperceptible, maybe it's like 10% or something like that. If it's 10%, you got all these switches in an Arduino, you could do synchronous rectification, which would be, there you go thinking again. But what you would do is you would leave nothing connected to here. I mean, you could have one line. Then you have this thing discharged to 0. That's where you want it. Now you break this line and you make a line out to here. And now it's shooting out here the same as if it would be shooting back here, and you don't have to worry about the diode. The diode, you don't need it. If you set it up that way, you break the line here and then just make the line at the same time that you break that one, you make a line to another cap. So that's going to have to be done, synchronous rectification. Now the other question I have, which I'm less certain whether I'll make any progress on it, but so here we're talking about the collapse of the magnetic field when it's going down, and you get this inverting DC-DC conversion where now you have negative showing up in either another cap or in this cap. That's from the magnetic field decreasing in strength. Is there a way, especially if you're using synchronous rectification, to also capture what's going on when the field strength is strengthening? That's magnetic field changing too. That's actually a boost circuit, as I understand it. And don't quote me again, I'm self-taught on this stuff. But you have two times that the magnetic field is changing. It strengthens and then it decreases in strength. And with this setup, you're only capturing where it's decreasing in strength. Is there any way to capture when it's increasing in strength? So I haven't done that yet, but that's another thing I'll look at. Okay, so let's do some work now. And so I just took this random coil and we're measuring the induction there. And it's saying that it's 13.47 millihenries. So I've set up this spreadsheet, 13.47. We put that in. Now we need the resistance. Now, okay, phone doesn't want to shut down. I don't like using this for resistance, so I'm going to confirm it with here, because if you do it on different frequencies, it changes a bit. Well, let's say 6.1. So 6.1 ohms, and I'm going to confirm that with the DDM, and we're using a 10 UF cap. So what does this little spreadsheet do? It calculates for us the tau time of the coil, L divided by R. So L divided by R is 2.2 milliseconds. And what does the tau time tell us? The tau time tells us the amount of time, if you had a constant voltage source, say, just a 10 volt, constant 10 volt source, the tau time at 2.2 milliseconds, you would be 62% of the way to saturation of the coil. And that's, if it had more induction, it would be slower, L divided by R. Or, it's a little counterintuitive, if it had less resistance, it would be slower. And it also calculates for us the resonant frequency, and 1/2 pi. And so here it's just giving you the time, and here it's giving you the hertz. And then here, this is actually the time this is 1/2 the resonant frequency. I just have it set up that way. So the reason I have it set up that way is that what this tells us is that if you connect the capacitor to here for 1,152 microseconds, then disconnect them, that's where the cap will be most negative. And half of that is where you get your best inductive spike, but we're not looking at that. We're just looking at where it goes most negative. Now, these are calculations. It's sometimes off by maybe like 5% or 2%, and it might be the measurements here. I don't know. It's usually, sometimes it's like dead on, sometimes it's a couple percent off. So let's fire that up and I'll show you. So now I've got the coil hooked up, I've disconnected this diode, so this thing's not doing anything. We're not shooting anything out to another cap. All we're doing is discharging this cap through the coil, and we're going to look at what this cap ends up at its most negative point. And so we have this code now, which is very simple. I'm just going to pulse it once, don't even need the for loop, and we're going to pulse it for on time, and I'm setting on time equal to 1152 microseconds. So there's our on time. We pulse it, then we disconnect it, and we see what it registers. I'm just seeing now that we're actually at 10 volts, so 10.01. Oh well. So all of this part happens in, you know, a couple milliseconds, and then I delay it for 3 seconds. And so what we see here is it goes to negative 7.42, 46, negative 7.46, right around there. And then, you know, for 3 seconds it's draining out, and then it cycles through that 10, negative 7, but that happens in a millisecond, so there's no time for anything to show up here. So all we're seeing is the most negative part. So that's pretty neat. Went from 10 to negative 7. And I also, I need to retract something I said previously, and sorry. I'd said that this, you know, if you have it hooked up to there, that it doesn't see it at all. It does. If you, like for instance, had this shorted, this wouldn't go to negative 7. It would go to like negative 0.5. And similarly, if you're going from, you know, like 0 to 5 or whatever, it doesn't go that negative. It's only if this thing is actually at or above your input voltage that this thing can still swing negative. So that makes things more difficult too, because it's kind of, I mean, more difficult in terms of how you want to engineer things, that it's not that straightforward. But, and this is something new for me. Well, first thing I'm going to do is I'm going to fiddle around a little bit with this timing, you know, increase it 20, decrease it 20, and see if we're spot on, or if we can get to, you know, like negative 7.5. So I'll do that and get back to you. So at 11:25 here, it's, I was seeing about 4.7. That was before 4. Maybe it's not any better. There I saw a 5. I think it's about 11:25 instead of 11:52. So as I said, you know, it's real close, but you can fiddle around a little bit. You know where essentially you want to be. So now I'm going to do something new. This will be new for me. And what we're going to do is we're going to reconnect this diode and shoot it out to here. We'll measure what's going on in this cap. And so if we divide this in half, and now we disconnect it at whatever that'll be, 661 or 2 microseconds, that will be the 0 point. And then the field, that's where the field is strongest. Then the field will collapse. And the same voltage should show up, that negative 7.4 or whatever, in this cap with one pulse. And if it doesn't, I would say that's losses over the diode. So I just threw that in the spreadsheet. We'll call it negative 7.46, somewhere around there. And now I want to shoot it out, divide this in 2, and shoot it out to the other cap. And it should be about the same. And if it's significantly different, I think that synchronous rectification might help with that. Okay, so now we have it set up where it's going to go to the 0 point, which is about 562 microseconds. And then these are disconnected, and this collapsing magnetic field gets shunted out to here. And recall, this went to negative 7.46, somewhere around there. This is actually kind of cool. It goes to 6.6 volts. So why did I say that's cool? Because we know there's a 0.6 voltage drop across the silicon rectifying diode. And so 7.6 plus 0.6 would take us to 7.2, which would be very close to 7.47. I'm going to fiddle around now with the timing for this one and see if I can get it a little bit better. You know, if you get it 0.2 volts better than that, then you say, well, that's all from the voltage drop across the rectifying diode. And that you wouldn't have that if you did synchronous rectification. So that's kind of neat. I'm gonna fiddle around, but if not, you know, maybe this particular diode has a 0.8 volt drop, or you know, maybe there are other things going on as well. But that, you know, I mean, that's not far off from what I would have expected. Okay, so I'm seeing the best there, maybe around like 525 instead of 562. I'll call it 6.7. So 6.7. And now if we go into our spreadsheet, put in the 6.7, and there was 7.46. Let's just add those. Equals this plus this. So negative 7.6. So 7.6 voltage difference. And I'd have to look up. I always thought there was a 0.6 voltage drop across the rectifying diode, but maybe it's 0.76. That seems to be what we're seeing. Okay, so, you know, if we went to 20 volts and then 40 volts, we'd see this, you know, it might not swing negative to 74.6%, might be at 20, 74.8%, and 75% at 40, and so on with that trend. But I think I've amply demonstrated that in other videos. So I'm not going to bother to do that there, but I probably will do it on my own. Just what I'm interested in is if I put it to 20 volts and then do this same thing, there should also just be the 0.76. That shouldn't be like 1.4, negative 1.4. It should again be 0.76 if it's the voltage drop across the diode. But I'll show you two more coils and maybe two different capacitors, and then wrap this up. So let's do a different coil. So now I've put in this coil, and it weighs maybe 3 pounds. It's much thinner wire. And given that it's much thinner wire, we now have 492 millihenries of inductance as compared to 13.47. So this will have to be great, right? But also look at that, 93.5 versus 6.2. So what's going to happen? So again, this thing gives us a resonant frequency and gives us the half resonant. You know, the half resonant where it's going to be most negative. So 6,965 microseconds is what we want for before we disconnect the LRC tank circuit. I had these two backwards. I was like, what's going on? But this is what we get with this coil. It weighs 3 times as much and has something like 30 times more induction. And it's only flipping negative to -5 instead of -7.6. So we're going backwards. But let's just put that in the spreadsheet. Negative, call it 507. Negative 5.07. And I didn't diddle around. I mean, maybe you get to negative 5.1. You know, if it's like at 35 or something, I'm not going to bother. It's within 1% or 2 of where it should be. So 6965. 6965. So that's that coil. Weighs more induction, more winds. Take you forever. I mean, I did that with a machine that I built that isn't a very good machine, but at least it worked for that. And negative 5.07 versus negative 7.46. So let's put on one other coil. So now I put this big 10 pound just still on the spool, 10 pounds of 14 gauge wire, and have it hooked up. And I guess again, I just copied and pasted. The induction is 35.5 millihenries. And the resistance now is 2.4 ohms. So that compares to 492 and 93 and the other one 13.47 and 6.2. So how is this going to do? And the other thing I'll just say, you know, in passing here, sure would be nice now to get rid of that 1 or 2 ohms of on-state resistance with the solid-state relay. Because now, you know, 2.4 to 3.4 or 4.4, you're adding like 50% or coming close to doubling your actual resistance from what you're just measuring across the coil. So it'd be nice to have an opto-isolated MOSFET with you know, maybe 20 milliohms or somewhere around there. I don't know what they exactly, but it's in the ballpark, I would guess. You know, like 10, 20 milliohms of on-state resistance. But all that said, what's this one gonna do? So this one is flipping negative to negative 9.11 volts, 9.12 volts, 13 volts. Uh-oh. 1. So let's call it negative 9.12. And again, the timing was as calculated. I mean, I didn't fiddle around with it. I just stuck in the calculated timing of 1,871 microseconds. I was going to throw in 100 UF instead of the 10 UF, but let's just double it with the 20 UF, and you can see the effect of pulse duration on the Q factor. So we need to now, I'll copy and paste it again. Copy, paste, and now we're changing the capacitance. That's 20 UF, and so our resonant, half resonant frequency is now 2645. So we'll go into the program, change it to 2645, and see how negative this one goes. So now, when we doubled the capacitance, it's only going to negative 8.96, maybe negative 8.95. It's far more dramatic with the 100. With the 100, it would go to like negative 6, 8.96, I guess it is. Negative 8.96 versus negative 9.12. And likewise, if we went to a 4.7 UF cap, we would do better than the negative 9.12. Now, the problem I have if I go lower than that, if I go to like a 1 UF cap, you can't get a reading. It just is too, it just drains out of the cap too quick. But so one of the things I was thinking was I would put like 10 1 mega ohm resistors. There's a 10 mega ohm resistor there, like double the resistance, and then all the values here would be halved, and that is, oh no, I'm not gonna. But what you could do, and I'll probably do this, is take like a 1 UF cap and say it goes to negative 8, and then just have another switch where you shunt that out to like 100 UF cap. And when you do that, when this thing is like under 1 volts, I think it's a different resistor network, you can get a good solid reading. So then you could extrapolate backwards as to what how far negative it swang with the 1 UF, and I think you can get away with a 0.1 UF cap too. So the capacitance makes a difference, big difference too. So to start to try to sum things up, you know, it's like, what the heck is going on? You have like a 1 pound coil. That one swang to negative 7 point. Is swang a word? I don't know. Negative 7.46. You had a 3 pound coil. It only went to negative 5, and then this 10 pound coil went to negative 9.12, and then with the larger cap, negative 8.96. So if you'll pardon a little human vanity, so this part is not real fun or easy to share, but I think it's correct. But then again, I've made mistakes, so you know, you'd have to do the work yourself. But I'm pretty sure this is a very good metric. What you're interested in, and there's one number on here that I haven't mentioned before, but it's calculated automatically, so I'll go in and highlight them. What was I doing there? I did that one twice somehow. Here's this and that. What's this number? This number is the ratio of the tau time divided by the resonant frequency. So, I mean, I'm no expert on Tesla or anything like that. You know, I've read like a few of his patents, a little bit of his notes. I'm not saying that I know much about him or what he did. But I will say, you know, one thing I was reading, he's saying, I'm looking at coils of high inductance and low resistance, and that stuck with me. So the tau time is inductance divided by resistance. So the higher the inductance and or the lower the resistance, the longer the tau time. High inductance, low resistance, long tau time. The resonant frequency is how fast your discharge is. And so the cap discharges at the resonant frequency. And so that rate of change is determining how fast the magnetic flux is changing in your inductor, and how fast and how strong a field and how fast it is changing per Faraday's law of inductance is how big of an EMF you get. So if we look here, this was the first coil, the small green one, and the ratio of your resonant frequency to the tau time was 0.53, and we got negative 7.46 for, you know, that's really, I would say, you know, it's a measure of the Q factor. That's how far it went negative. Now then we had 3 or 4 times, you know, the pounds of wire, massive inductance for, you know, for me, 492 millihenries, all this resistance. Now look at what happens because of the resistance. Your tau time is only modestly better, you know, 5.26 versus 2.17. Where am I? Sorry. But now your resonant frequency, how fast the cap is discharging, is 6.96 versus 1.15 there. So that ratio is now up to 1.32 and negative 5.07. Now we go to here with the big 10-pound coil. The inductance is only 35.5, but the resistance is now 2.4. And you know, now the resistance, as I said, of your switch will be coming into play. But just using those two numbers, because the resistance is so low, the tau time is bigger than either of the other previous two coils, even though with one of them it had more than 10 times more inductance. But again, the tau time is determined by inductance divided by resistance. So as resistance gets lower, this becomes a bigger number. And your resonant frequency likewise is fast because the R, you know, square root of R times, square root of L times C, the resonant frequency is fast. So 1.187, 14.97, and that ratio is 0.12 instead of 1.32, and you're at negative 9.12 now. And again, if the resistance in the switch wasn't there, it would do a little better. What happened when we doubled the capacitance? Well, now the tau time stays the same because capacitance doesn't factor into the formula, but the resonant frequency slowed down to 2.65 versus 0.126. And if we had gone to 100 UF cap, we would be looking at behavior similar to this, but now it just, you know, that ratio went from 0.12 to 0.17, and we see it's a little bit worse. So here I just have a fresh page, and I'm just doing like a hypothetical coil. So because now we can diddle around with it and look at what happens with this ratio of the tau time divided by the resonant frequency. So let's say you had a coil, and you know your cap's going to stay at 10 UF. It has 10 ohms of resistance, 100 millihenries, and you have this 0.314. Now, one of the things that really surprised me is that if this is correct, then throwing wire at it does not, it won't make things better. And we saw that it can make things worse. We tripled the mass of wire, yet we had something that was worse. So let's say we double the resistance to 20 ohms using twice as much wire. Now what happens to the inductance? I had to do this on a calculator. I mean, look this up on an inductance calculator. You would know that, you would have twice the length of wire, twice the resistance. You would have double your amp turns, but we're not worried about amp turns. We're worried about inductance. So what happens to inductance? And when you plug this in the online calculators, you see it goes up to 400, not 200. So what's the ratio? 0.314. Let's set it back to 10 and 100. 0.314. So that I find is interesting. Let's make the cap 1 UF. 0.099. And if you look at it, we went from 10 to 1. If you take the square root of 10, it's, I don't know what it is, 3 point something, 3 point whatever it is. And then you divide 0.314 by the square root of 10, then you get that. But see, that's better than, that number now is better than anything we had before, just going to 1 UF. Now, how else, let's go back to 10 UF, how else could you improve it? Well, I mean, one way is, like, for instance, with this coil, if I wound it, more flat like that, you're going to stay at 10 ohms, and, this will go to, like 120 millihenries. So you want to get the maximum inductance you can out of a given length of wire. Let's put it back to 100. But another thing you can do is you could just say, well, let's use wire with half the resistance and just put the same number of winds on to get to 100 millihenries. So now we make that 5, and this is now 0.157. So the resistance is not going by the square root. The resistance is going directly 1 for 1. The resistance was halved. This ratio was halved. Let's put it back to 10. And again, I'm going to have to confirm all this, but you could also say, all right, let's use thicker wire such that you had 10 ohms and 200 millihenries. You see, it doesn't have. It's going by a square root thing, not a direct thing. So 100, 3.14 to 0.22, and if we do this there, then 0.157. So the upshot of all that is resistance is very, very important. So what's the last piece of the puzzle here? And that is that you might say, all right, instead of 14 gauge, let's go with 10 gauge. That'll probably have less than half the resistance. What's the problem there? Now, we see the improvement when you go like from a 100 UF cap to a 10 UF cap. Then I'm going to document it from a 10 UF cap down to a 1 and down to a 0.01 UF cap. And that's your sharp transient. As you start getting that thicker and thicker wire, then skin effect begins to play a much bigger role. So we could go to a skin effect calculator, but I'd say somewhere around 120 UF. If you were oscillating AC, that would be a big problem with this 14 gauge. And so you want thinner wire. But if you use thinner wire, you have more resistance. But you need to cut down the resistance, so you go with thicker wire. But then you can't go with as fast a small a cap for as fast a pulse as you want. So what do you do then? Well, back when John Bedini had his store, I bought two things. I bought this little toy, like 3 magnets on the end, pulse machine. You're getting the spike out. And then I bought one of his coils that he has like this. And this is Litz wire. So you use Litz wire where it's the they're all wound around each other. They're not here, but they are when you get into the coil. They're all wrapped around each other. And this distributes the skin effect. So now you can pulse at the rate of one of these. You can pulse it really quick, but he's got 8 of them here. So this wire is way thicker even than the 14 gauge. It has much lower resistance. I measured it, in this coil has something like 1 millihenry. I think that was probably on purpose. 1 millihenry, and I think it's either between 0.2 or 0.4 ohms of resistance. So now, you know, that switch with 1 or 2 ohms of resistance is not going to cut it, because now you've got 5 or 10 times more resistance in your switch than you have in your actual coil. But this, it seems to me, would be the way to go. I'm surprised John was right. And now you can go fast, you know, real sharp transient, and you have very little resistance. And so, you know, you could go ahead and make it a big coil if you want to get more induction, and you know, you can have arbitrarily, you know, within reason, arbitrarily low resistance, and then be able to pulse arbitrarily fast. You know, I don't think it would be much fun to, you know, have 100 wires of you know, like 24 gauge or something like that you're trying to work with. But that's the idea. The other drawback of this Litz wire is just ridiculously expensive, so it's a pain to figure out how you would do it. But you probably just want to make some yourself, and you know, you probably, you know, you don't need all 8 of those. You could just you know, even have like 3 strands or something, and you'll still get improvement. So that's it. Now you know the rest of the story. And you know, maybe I'm wrong on these things, but again, I'm going to be continuing to investigate. And, you know, what are the things to do going forward? I think one of the main ones is to be able to get a better switch, and I ideally will be able to opto-isolate a MOSFET. I know they have prepackaged gate drivers, but that's kind of overkill for what I'm trying to do. Although at some point I should look into that. And if I can't opto-isolate a MOSFET, at least opto-isolate a BJT. If worse came to worse, just repeat the way John Bedini did it with the bipolar commutation circuit, because that also would be an avenue that should work. What are the other things to work on? We want to build a charge pump, you know, voltage doubler. And so, you know, if this is going to 50, then you could go to 100 volts. If it's a stupid idea, but you know, I put those in series and it works, so that's like 110 volts. Then you get out to 220 volts, and so you start to get out to a bit more voltage. Oh, and the other thing is to look at synchronous rectification, and you know, we don't need this stinking diode. Get rid of the diode. And the thing that I'm curious about there, and I don't know whether I'll have success or not, but as I mentioned before, you've got 2 fluxes here. You've got when this thing is charging up, going from 0 to charging up, and that would be non-inverting. And then you have when it collapses, and that's the inverting that shows up as the -8 there. Okay, I got a message that I ran out of storage space, so I think that's telling me something. But just to finish up, I was saying the third thing would be to do the synchronous rectification and see, can you gather the induction one when the inductor is charging up as well as when it's collapsing. And I don't know whether that can be done or easily or not, but those are the things I'm going to look at going forward. And I think the first one is going to be trying to get an opto-isolated MOSFET. So thank you for your time, and I hope that people find this useful and enjoyed the presentation as well. Ciao for now.